Let's look at an enterprise refund agent tasked with a standard customer request, finding out where their order is. Behind the scenes, the agent attempts to fetch the record, but hits a transient 2-second database timeout. This diagram maps the query. The database flags a timeout, but the tool swallows it, returning an empty array and a green 200 OK. The model absorbs the array, concludes the order doesn't exist, and tells the customer. Unbroken logic built on false data? The standard engineering reflex here is to add infrastructure. We bolt on a routing classifier, write a complex retry loop, or add a sterner system prompt, begging the model to be careful. None of those address the core defect. You cannot prompt a model out of a hallucination if the tool it relies on is feeding it a false reality. This exact scenario is tested heavily on the Claude Certified Architect exam. It enforces a strict design thesis. Advanced reliability requires fixing the tool interface itself, not the prompt. An agent is only as reliable as the data its tools return. If a tool lies about an error, every downstream decision becomes a confident hallucination. To prevent these silent failures, an agent needs to perceive when its operational path is interrupted. In a typical Python script, a failed database call might trigger a standard try except block, throwing a bare, uncaught exception straight back to the execution layer. When that raw exception hits the agent loop, it instantly terminates the entire run. The model gets zero opportunity to reason about what went wrong or attempt a recovery. This animation contrasts that fatal crash with the Claude Agent SDK's requirement for structured error contracts. On the left, the red execution path shatters abruptly at the exception block. On the right, the green path catches the error and packages it into a neat JSON envelope. That JSON envelope contains specific actionable data. It labels the failure category, includes a Boolean flag indicating if the error is retryable, and returns the original attempted query. Crucially, it also sets the isError flag to true. That specific Boolean forces Claude to read the return as an explicit operational failure, rather than just oddly formatted database output. Returning a structured error contract transforms a fatal crash into a manageable data point. It keeps the agent loop alive, so the model can strategize a recovery. There is a strict architectural danger in collapsing two completely different negative outcomes into a single opaque return. This decision tree illustrates the first outcome. A data request hits an API timeout or rejected credentials. The left branch leads to a distinct red node representing an unknown world state. In an unreachable state, the world is currently unknown. The tool must signal a definitive error, so the agent knows to halt and retry. Contrast that with the right branch. The execution succeeds, but it legitimately finds zero matching rows in the database. This is a known empty state. Because this is a trustworthy fact, this successful empty state must return an empty list without an error flag. Conflating an unknown world with an empty world is the exact mechanism that triggers irreversible hallucination. Separating these two states is the cheapest, most effective reliability fix in agent design. Consider a scenario where our agent routes order queries to a getCustomer tool instead of the getOrder tool nearly half the time. The instinct here is to add an external routing classifier model to manage tool selection, but that is an architectural anti-pattern. The model already has a router. The tool's description metadata and input schemas serve as the built-in routing layer for the agent. Look at this gray block representing a Python tool decorator. The description reads, "Get customer details," and takes a generic ID parameter. It completely fails to provide necessary routing signals. A robust description requires explicit definitions. It must state its exact purpose and declare the specific return format. It also needs a negative routing signal. We explicitly state what the tool is not for and name the correct alternative tool right in the text. Finally, renaming generic parameter strings to domain-specific schemas provides the last layer of disambiguation. Misrouting is a semantic boundary failure. Tightening tool descriptions completely eliminates the latency and cost of running a secondary classifier model. Beyond defining individual tools, we also control execution constraints applied at the API level. We manage this with the tool choice parameter. Setting this dial to auto gives the model maximum latitude, allowing it to choose between a tool execution or a plain text response. This is ideal for open-ended conversational, when a plain text reply is unacceptable, setting the dial to any forces in action, directing all data flow exclusively through the tool execution path. When the system requires deterministic, unimprovised execution, we lock the dial to a single specific tool. The data flow bypasses all model deliberation. There is an architectural limit on how many tools an agent should have access to at once. This line graph maps routing accuracy against exposed tools. Community data shows a severe degradation cliff occurring when a single model is exposed to more than 18 similar tools. The solutions to tool bloat are aggressive pruning, strict namespacing of related tools, or utilizing a discovery mechanism so the model searches for tools rather than scanning an overstuffed list. Constraining both the model's latitude and its menu of options guarantees deterministic routing without ever relying on the model to just figure it out. To expose these optimized tools to the agent, we rely on the Model Context Protocol, or MCP, as the foundational wiring layer. At the root of the project sits the DMCP JSON file. This configuration file manages all shared server declarations. This JSON tree shows the two primary MCP server structures. The first node defines a local process using command and arguments. The second node declares a remote process using a type and URL. There is a strict security constraint here. Plain text secrets and API tokens must never be committed to this file. Instead, we use environment expansion syntax to securely inject variables at runtime, passing tokens right from the environment. Setting fallback defaults within that expansion syntax ensures local development stability without ever compromising production credentials. Properly configured MCP wiring ensures that the legible, well-described tools we designed remain securely connected to their underlying data sources across any deployment environment. Let's look at the complete architecture. Data flows seamlessly from a secure MCP configuration block through a constrained list of highly described tools and loops cleanly back to the model via structured JSON envelopes. This brings us back to the central rule of the exam. When faced with an agent failure, choose the interface fix over the prompt fix or the infrastructure fix. The underlying model's reasoning engine is rarely the broken component in a misbehaving system. By guaranteeing tools fail legibly and keeping semantic boundaries tight, engineers build systems whose logic can be trusted. True AI architecture is not about begging models to behave in plain text. It is about building rigid, unforgiving contracts that force them to succeed. If you are building at this level of complexity, subscribe here and follow me on LinkedIn, Substack, and Medium for continuous architecture deep dives. And if your enterprise needs to transition from brittle prototypes to robust agentic systems, reach out to Spillwave using the links in the description below.